Alright, in this lesson we're going to start looking at circuits and talk about Ohm's law a little bit later on in this lesson. So a few quick definitions that we kind of need to talk about as we get into looking at circuits. The first one is charge. Charge is measured in coulombs. It's basically the amount or how positively or negatively charged something is. It's the amount of positive and negative charges that have been moved from one place to another. We give charge the symbol Q. Not really sure why it's given the symbol Q, just happens to be given the symbol Q. For the sake of comparison, one electron has a charge of negative 1.602 times 10 to the negative 19th coulombs. One proton has a charge of positive 1.602 times 10 to the negative 19th coulombs. The second value that you come across quite frequently when we start talking about circuits is voltage. And what voltage really is, it's an amount of energy per unit of charge that's being transferred. It's more related to potential energy. How much energy is that charge carrying? It's measured in the units volts, and 1 volt is defined as 1 joule of energy per coulomb of charge. The third value that you come across quite frequently is current, and we give current the symbol I. And what really current is the rate at which charge moves through a circuit. It's measured in amps or amperes, and 1 amp is defined as 1 coulomb of charge per second. The other term that we come across quite frequently when we start talking about circuits or electrical devices is resistance. And really what resistance is, it's a measure of how hard it is for charges to move through a material. Generally speaking, if resistance increases, current decreases. It's dependent on a couple of different things. It's dependent on the material. Some materials are generally fairly low in resistance. We call those materials conductors. Here there's a whole bunch of conductors near the top. A lot of them are pretty common things you would think of. Metals. Some of them have some materials have very high resistances. Those we would call insulators. It's also dependent on the geometry of the material. Both the length, longer wires tend to have more resistance because the electric current has to go through more of that material. And cross-sectional area, A, also plays a role. Happens to work out as cross-sectional area increases, resistance decreases. I usually think of resistance as being more of a surface effect on current carrying wires. So the greater A is, the more room there is for current to move through a circuit. So we have a relationship between resistance and then a value that's called resistivity, which we give the symbol rho to. That basically is dependent upon what material you're talking about. L is the length of your wire or your substance, and A is its cross-sectional area. The third rule that we have the next rule that we have is what's called Ohm's law. And Ohm's law gives a relationship between resistance, current, and voltage that works very well in lots of different types of electrical devices. Anything that we would generally consider to be a resistor in an electric circuit, which basically is something that resists the flow of current, follows Ohm's law. It's a very useful relationship for many types of things and many types of circuits. A device is considered ohmic if it follows Ohm's law. The last relationship that we want to kind of come up with is a relationship for electric power. Now we know that electricity carries energy. Obviously that energy can be converted to a variety of different forms after it gets used up. And so power, the rate at which energy is being consumed, is sometimes a useful way to talk about electrical devices. Now if you look at the definition of power, 1 watt is equal to 1 joule per second, and we use the definitions of current and voltage, that 1 volt is 1 joule per coulomb, and 1 amp is 1 coulomb per second, it becomes fairly clear that if I take an amount of volts and amount of amps and multiply them together, I should get power. That 1 watt is also 1 volt times 1 amp. You can actually show this by taking a joule per coulomb, multiplied by a coulomb per second, you end up with a joule per second. So the equation for power that we could have is power is equal to current times voltage. Basically, how quickly charges move through times, how much energy there is per unit of charge. Which if we think about it kind of makes sense. V talks about how much energy there is per unit of charge. I talks about how many charges move through in a unit of time. If we apply Ohm's law and plug in IR for V, we get that it could also be related to I squared R in a resistor. Or if I plugged V over R in for I, we could get V squared over R is also a way to calculate power. So there are three ways we can calculate power depending on if we know current, voltage, or resistance. So let's do three example problems. The first one, we have a battery pack in a calculator has a voltage of 3 volts. It delivers a current of 0.17 milliamps. And it wants to know for 1 hour of operation, what is the total amount of charge and energy delivered by the battery pack. So the known piece of information is we know that the battery pack has 3 volts, that the current is 0.17 milliamps, which is the same thing as saying 1.7 times 10 to the negative 4th amps. Basically take your 0.17 and divide by 1,000. And the time is an hour, which is 3,600 seconds. We don't know Q and we don't know E, energy. We do know relationships for Q, T, E, V, and I. That I is equal to Q over T, basically the current is equal to charge over time, and the voltage is equal to energy per unit of charge. So I'm going to solve for charge first. If I solve for charge in the first equation, I get I times time equals charge. If I solve for energy using the second equation, voltage times charge gives me energy. So if I do a quick calculation, I can calculate the amount of charge by taking current and multiply by time. So I get 0.612 coulombs of charge got delivered. If I take 0.612 coulombs and multiply by 3 volts, I get the amount of energy, 1.836 joules. So these two relationships can be helpful in a way of converting using time and charge to find current, or energy and charge and voltage. Example problem 2, we have instructions for an electric lawnmower suggest that a 20 gauge wire can be used up to a distance of 35 meters, but a thicker 16 gauge wire should be used for longer distances to keep the wire's resistance as low as possible. It gives us the cross-sectional area of a 20 gauge and 16 gauge wire, and it wants us to determine the resistance of a 20 gauge copper wire that's 35 meters and a 70 gauge copper wire that's a 16 gauge copper wire. So for the 20 gauge wire, we know its cross-sectional area, we know its length, and we can actually go back in my table for resistivities and look up the resistivity for copper. Now the reason I've picked copper wire is that copper is a pretty normal wire that you would use. So what is R? Well, we can actually calculate R by doing resistivity times length divided by A. If you plug in those numbers and do the calculation, you get that the resistance of this 35 meter long wire is 1.2 ohms, which, if you maybe could have guessed, is not that large of a resistance, especially for a wire that's 35 meters long. Do the same thing for the 16 gauge wire. The two things that change are A and L. Again, I don't know R. Here's how I could calculate R given the information I know, and so 0.99 ohms. So by changing from a 20 gauge wire to a thicker wire, 16 gauge, we decrease the resistance even though we doubled the length. One thing to point out about wire gauges is that the weird thing about wire gauges is that the way the system is set up, the smaller the gauge number, the thicker the wire is. Why that is, I'm not really sure. It's just the way the system has been set up. The third problem that I have is the filament of a flashlight bulb acts as a resistor in the form of a very thin wire. It becomes very hot, and in fact hot enough to emit light. The reason why the filament in a light bulb lights up is that you've heated up the wire so much that it actually begins to expel electrons and photons light. Flashlight uses two 1.5 volt batteries, which effectively operate as a 3 volt battery and provide a current of 0.4 amps. Now, what is the resistance of the filament? Well, here I can use Ohm's law. V equals IR, solve for R, plug my values in, and I get 7.4 ohms as the resistance of the filament. I could also calculate what the power of this light bulb is. 1.5 times 0.4, there's the power output of this light bulb. So it's kind of a quick overview that introduces us to some circuits and some basic terminology and talks about Ohm's law and what Ohm's law really means.